In this video, we'll discuss confidence intervals and prediction intervals for values that we predict using the regression equation. So as a reminder, we can get the predicted response by plugging in an x value that we want the predicted response for into our model using our sample statistics and doing the calculation to get the predicted outcome. What is interesting about this particular predicted outcome is that this predicted outcome is the average or the expected response. So this is kind of the middle of the response that we would expect for the y's to be. However, there is variability around this. That is to say that there is not a guarantee that this is going to be exactly the right answer. And we already know this. Again, there's error enveloped in the model. So what can be nice is if we're trying to predict this response or predict the average response, we can construct a confidence interval for the average response if we use the variances from the intercept and from the slope. So the variance associated with the predicted average response. Now, this is a predicted average, so let's think about what we're predicting here is if I did this over and over and over again, what would the mean be? So let's say we have, so one of our examples is the time it takes to run the 40-yard dash and the NFL rating at an NFL combine for a prospect. So if I'm saying that the time it takes to run a 40-yard dash, let's say we predict that if you run the 40-yard dash in 5 seconds, that your NFL rating will be, I don't know, 60. I don't really know. But let's say we predict it'll be 60. When we're discussing predicting the mean response, what we're saying is if we had a whole bunch of people run the 40-yard dash in 5 seconds, what would their average NFL rating be? So that's what we mean when we're talking about predicting the mean response. So the variance associated with the mean response is just the variance from the associated with the intercept times the variance associated with B1 times X. Now, if you remember from your math stats course that the variance of B1 times X, we can pull out the constant and square it. So this is X squared sub H constant times the variance associated with B1. Now, we already know what the variance associated with B0 and the variance associated with B1 are. That's what we covered in our previous lectures, or our previous videos in this lecture. So we can reduce all this to be the sigma squared, the error variance, times 1 divided by n plus x sub h minus x bar quantity squared divided by the sum of squares of x for all of the x values in the data set. So we substitute the MSE in for sigma squared, just like we have in our previous equations, to get the estimated variance of the predicted mean response. And again, this is predicting the mean. And then we take the square root to get the standard error. So if we get we have the variance, this is the variance, simply take the square root of the variance to get the standard deviation. And recall that the standard error of a variable is literally the standard deviation of a variable. Standard error is just another way to say standard deviation using the sampling distribution. So for the confidence interval, recall, now that we have all this, that the confidence interval general formula is the point estimate plus or minus the critical value times the standard error. In this case, the confidence limits are the standard error of y hat, the standard error is the standard error of y hat, the critical value is t crit, and we've already done the critical value, so the only thing new is what we derived in the previous slide, which is the standard error of y hat sub h, the predicted mean value at x equals h. Now, sometimes we want to predict a new observation. That is, we don't just want to predict what the average value will be. So we talked in the previous lecture, lecture 1, about predicting a single point. We've talked just now about predicting the mean. Now we're going to talk about predicting a single point, but coming up with an interval for that prediction. So we just talked about the interval for the mean prediction. Now we're going to talk about the interval for a single point prediction. Now, the interesting part about this is that there's additional variation associated with the point when we're looking at an individual observation. So what you can think about is that the mean varies because there's a random variation, and that's what we just did in the confidence interval. But for the prediction interval, we're going to add additional variation onto the fact that a single point deviates itself from the mean. So we have the mean variation, that's what we just did, but now we're going to have additional variation because the single point deviates from the mean. So there are two components to this: the variance associated with the mean response, which is what we just looked at, and the variance associated with observations around the mean. That's this additional variance component that we have to account for. The variance associated with predicting a new value or a new point. Now, I use the notation y hat sub h new, and that's to distinguish between y hat sub h, which was the mean value. Both of these can be for quote unquote new points, right? They don't have to be for pre-existing x, though remember you need to keep x inside of the range of the observed x values to avoid that extrapolation problem, or you have to or you have to be close to the range of x. But the variance associated with this, the notation, I use new to indicate that we're predicting a new individual point. So the confidence interval for the mean prediction, that's what we were talking about previously. Now we're talking about a prediction interval, which is for an individual point. So that's just a definitional term that when I talk about the confidence interval for prediction, that's the mean. And when I talk about the prediction interval, that's for a single point. So what we have is we have that same variance formula that we looked at earlier, but now we have to add this additional sigma squared. So when we work this out, we recall had sigma squared times 1 over n plus this fraction previously. Now we just have an additional 1 plus, and that's from factoring out the sigma squared in this first component too. As before, we simply substitute the MSE for sigma squared and take the square root to get the standard error of the y hat sub h new, or this is the standard error of predicting, again, a single new point. So we had three things. We predicted the point and got our point estimate. That's our single best guess number. We did that in lecture 1. Previously in this video, we talked about coming up with an interval for that prediction if that prediction is for the mean response, and we had that. The standard error was the square root of the variance of y hat sub h. And now we just talked about doing a prediction interval with the standard error of prediction, which is the square root of all this mess. And that is for predicting a single new point as opposed to predicting the mean value of those points. Now, this will always be wider than the confidence interval. So the confidence interval for the mean response will always be narrower than the prediction interval for an individual response, and that's because the prediction interval has this additional variation component that's associated with how much each individual value deviates from the mean. The whatever percent prediction interval for a new observation is given by this formula, and again, this formula should look boringly familiar. It's the point estimate plus or minus the t-crit times the standard error. Note that the point estimate for confidence intervals and prediction intervals is the exact same. This is our best guess number, and it's our best guess number for the mean. It's our best guess number for a new data point. So this best guess number doesn't change. What changes is how variable this is. So if we're estimating the mean, recall from the central limit theorem that mean standard deviation is not as wide. It depends on things like sample size and so on. However, when we're estimating a new point, we have to take into account that new point has additional variation, and so it changes the standard error. So the only thing that's changing between confidence intervals and prediction intervals are A, the interpretation. Confidence intervals are for the mean response. Prediction intervals are for predicting a new point, what interval that point could fall within. And the standard error in the formula, that's the only thing that's changing because y hat sub h and t crit are actually identical in both formulas. So I mentioned extrapolation earlier. Extrapolation is the process of using the models to predict data, assuming that the pattern continues. So think, if you will, I've got a certain data set and I've got a line of best fit here, and then I want to predict a point that's way up in the top corner. Well, if I've only got data on this line, I could just kind of pretend that that line continues up and assume that it's going to land somewhere up in here. But, well, that may or may not be acceptable. So if we're looking at data that's really clustered around a particular range of x values, we can do we can extend it a little bit outside of the range of the x values we've seen. But if you go really far beyond, you're making some really big assumptions about how your data behave at extreme values. Now, this is very important when we start dealing with fancier models, because as we deal with models that can allow like curved lines and stuff like that, if I assume that the line stays straight, but what really happens is that it flattens out after a certain point, if I make my prediction based on it staying straight, it's going to be very different from the true value, where that value may flatten out. So we want to be careful. And the problem with assuming that the pattern's going to keep going, even at extreme values, I've been illustrating with my little mouse here, extreme positive values, but it could also be extreme negative values. Let's say our data's up here, and then I assume the values go back to these extreme negative values, or values extremely far below the range of the x values. That's a problem too. In fact, when we talk about cases where x equals 0 doesn't make sense, it's kind of a special case of this. In fact, you may have a homework problem that asks you to write about that. But think about why that's a special case of this and why that doesn't necessarily make sense. So the rule of thumb is to stay, when we're doing predictions, whether we're doing predictions for a point prediction, just a single number best guess, if we're doing interval predictions where we're looking for a confidence interval of the mean response, if we're doing prediction intervals where we're looking for an interval or an interval reflecting the an individual point response. For the x values that we're doing predictions for, we want to stay close to the range of the observed x values. So if all my data is indicating a line up here, I don't want to go very, very far below that, because that assumes that the line stays constant. It assumes that the pattern continues beyond the range of my x values. Two reasons I don't want to do that primarily are A, that it assumes the pattern continues, but B, it assumes that those x values are reasonable, and that may or may not be true. I mean, if we did a data collection and only these particular x values were observed, why on earth would I assume that an x value way over here would be a reasonable value if all of my data suggests that the x values are in this particular range? Now, there may be an x value that's slightly bigger than that range or that's slightly smaller than that range. So that's okay if we stay close to the range of observed x values, but jumping far beyond that tends to be not supported. And this is, again, especially true when we start fitting fancier models, but true when we're dealing with simple models if we're modeling complex situations, because, again, distributions may tail off, they may increase, they may drastically increase. I might think there's a relatively mild slope, but maybe later on in the distribution it takes off in an exponential curve. But if I extrapolate my mild slope out, I would be very, very far off in terms of predicting, whether I did a point prediction with the single number, a confidence interval prediction for the mean response, which would predict the average value at that x value if I did a whole bunch of trials at that x value, or if I did a prediction interval trying to predict a point response. All of those would be pretty far off if the pattern changed, and I wouldn't know anything about that unless I had x values there to indicate that the pattern changed. So we stick close to the range of our observed x values to avoid the problem of extrapolating in regression prediction. All right, so in the quick recap earlier, we talked about all of these different parameter estimates, but now let's talk about their standard error. So the standard error of beta 0 is square root of MSE times 1 over n plus x bar squared divided by sum of squares of x. So this is our standard error of our intercept. Standard error of the slope is just the square root of the MSE divided by the sum of squares of x. The standard error of y hat, this is the standard error of the mean prediction. So recall, standard error of mean is different than the standard error of the point, because the point has both mean variability and point variability from the mean. The mean just has the mean variability, and that's this equation. And then the standard error of prediction, which allows the point to vary on top of the mean, is this one. Note how similar many of these things are, that in this particular case, what we're dealing with is the MSE times some value, and the value changes. So up here we have x bar squared minus the sum or divided by the sum of squares of x. Here we have the predicted value minus x bar squared divided by the sum of squares of x, and here we have 1 plus all that. So these are very, very similar, and you can see how these build on top of one another when we're calculating these different standard errors. And again, sometimes it's nice to have them all in the same place. Now, sometimes, again, you can look at error as white noise. So one question that can come up is not just how do I increase my sample size, that's always good, or excuse me, how do I increase the validity of my test, but how do I minimize the standard errors? So the first one is what I just mentioned earlier. You can increase the sample size. So we can use power analysis to figure out maybe what sample size is needed, but if you want to minimize the white noise or the error, then increasing the sample size minimizes the white noise or the error. So if you go back to this previous slide, all of these, except for the slope, incorporate, and actually the slope does incorporate this just behind the scenes, but all of these incorporate 1 divided by n. So if n gets larger and larger and larger, this fraction gets smaller and smaller and smaller. So we can increase the sample size to decrease all of our standard errors. Now for some of these standard errors, you can also increase the sum of squares of x. You notice that all of these fractions also have a divided by the sum of squares of x. So if I increase the sum of squares of x, then that decreases the standard error. So that's another option that you can do, is spread out the x values a little bit wider, and that gives you a bit of a smaller sums of squares of x. The last thing that you can do is, if you're doing prediction, you can predict close to the mean x value. So the closer your prediction is to the mean x value, the more accurate your prediction is going to be able to be. Let's think about this. If I have a whole bunch of data in this particular range, it would make sense that if I make a prediction in the range where I have a whole bunch of data, that prediction is more accurate than if I make a prediction in an area that I don't have very much data at all. That is what this last bullet point is getting at, is that if you predict close to where all your data is, it's going to be a more accurate prediction than if you predict far away from where all your data is. Now that's built into our equations. You'll note that the difference for these two prediction equations, the mean prediction and the single point prediction, both incorporate how far the data point you're predicting is from the mean of the x values. And if it's really far away, well, then this particular value is going to be really high. You're going to have a lot of white noise. You're going to have a lot of potential for error. But if this value is really close to all the rest of your data, or really close to the mean of your x values, then you're going to have a lot less white noise, because that's where all of your data are located. So in this particular case, that's a third way that you could minimize error if you're designing an experiment and you really want to have as little white noise as possible. You can increase the sample size, you can increase the spread of your x values to increase the sum of squares of x, and you can arrange for the prediction to be as close to the mean x value as possible. All right, on the next episode, we will talk through the confidence band for the whole line, the working hoteling band. It's kind of an interesting idea. What if you want to predict not just a single prediction, but you want to make a whole ton of mean predictions? You want to do mean predictions for the whole darn line. We will talk about how to do that. We will talk about the ANOVA table for regression. We will talk about the general linear test, and this is actually a really cool, really huge test that we will really like, because it is extraordinarily flexible. And then we will talk and revisit the correlation and the coefficient of determination interpretations that I know we've already talked about these, but we will revisit them once more from a regression framework.